Hello friends. In the previous session, we have gone through the Norton's equivalent and we have done some simple problems on Norton's equivalent. Now in this session, we will be doing a couple of problems on Thevenin and Norton's equivalent, in which I will be introducing the dependent source as well. Alright, so let us take things easy. Let us start with a simple problem. So this particular network you are having here, you have to find the Thevenin equivalent of that network. Note that here there is no load which is given. So you have to you have to assume that there is going to be some load which is going to be connected at this point and this point. So you have to find the Thevenin equivalent of this circuit. Alright. Yeah, let us begin. So first is assigning of network A and B. So network A is this entire area here. So this is your network A and network B is not given. So this is a black box which will go and get connected to any circuit, right? So let it be there like. So you have assigned the network A. Second is the finding of VOC, which is equal to VTH, which is this particular voltage. All right, it is that particular. Let me just rub to make things more easier. Yeah. So it is this particular voltage VOC, which is equal to the Thevenin voltage. All right. So let us how we can find it. So this particular voltage is VOC here. Because there is no current which is going to flow through this particular area, so the same voltage will come here. All right. So this is also VOC. All right. That means this is also VOC because there is only a single wire connecting. So I can use my trusty node voltage technique here. So let me use it. So VOC minus 3 divided by 2, which is this particular current, and the 7 milliamperes is going down. Now because this it is given as 7 milliamperes, I am putting this 2K, which is 2 directly, because volts divided by a resistance in K will give it in milliamperes. So it's a thumb rule. All right. In case they had given it in 7 amperes, I should have converted it into 2000 ohms. All right. So that will go in the next question also. There is an interesting question. So this is in the downward direction. So plus 7, and next is this current, right? So it is plus VOC minus 0 divided by 5. All right. So, and there is no current which is flowing through this area. This current is 0. So that total KCL is going to be equal to 0. So from this what I will get is that 5V minus 15 plus 70 plus 2V will be equal to 0. So this all OC is going to come here. That means I will get VOC to be equal to V Thevenin. This is equal to minus 55 by 7. It is minus 55 by 7, or it is equal to minus 7.85 volts. This minus sign is there. Let us keep it like that. Don't try to change. All right. The next thing which we have defined is the Thevenin resistance. So let me just rub things a little bit so that things become more clear. I'll just rub these current values also. Not required. Yeah. So you have to find R Thevenin as you see it from this terminal. All right. Open circuited terminal. So what I have to do, I have to kill the current source. So I have replaced it with an open circuit, and this I am replacing with a short circuit. I'll just show that current source here that I have replaced it. So this is going to be a short circuit here. All right. So let us see what is happening. Let's rub all these things. Yeah. Okay. So clearly what you can see is that, don't forget this resistance here. So this point is common to the 2K and 5K. And this point is common to 2K and 5K. All right. I think this is dirty here. I'll just replace it properly. It's always to be neat rather than sorry. Yeah. So now it is better. This also I'll just redraw it. In competitive exams, you won't get time to redraw. So you have to understand all these things in the mind itself. So now this point is common between 2K and 5K. All right. And this point is also common between 2K and 5K. All right. That means 2K and 5K are in parallel. So RTH will be equal to 2 parallel 5. And the effective value will be in series with this 1K, right? Because this is going to be replaced by a single resistance, 2 parallel 5. And that is 1K is here. And you are seeing it from this side. All right. So plus 1. So you will be getting 2.428K. All right. Now, so what is the Thevenin equivalent? Don't change the polarities. Put as you know. All right. Just put it like this and just replace it by minus 7.85 because you have got a minus 7.58 volt. Don't try changing all these things. In case your teacher asks to change these things, or asks you to put a positive voltage here, just replace this minus by a positive and the positive by a negative sign. But otherwise, this is well and good. 2.428. Ultimately, the concept is important, right? Not the how you arrange the voltage elements and all this. The concept is important. So this is the solution. So what will be the Norton equivalent? Norton equivalent, I will just put it here directly. So this is 2.428K and this will be minus 7.85 divided by 2.428. I'm sorry, I made a blunder here. Norton equivalent is always a parallel connection, right? 2.428K. Alright, so this is going to be my Norton's equivalent and this is my Thevenin equivalent. I hope you have understood this problem. Now let us move to the next problem, which is the important problem which I have been waiting for to do. Yeah, we have to find the Thevenin equivalent of this particular circuit. Now it has a dependent current source which is dependent on this particular voltage. So you must not change the sign, nothing you have to do. Keep that there. Depending upon the circuit condition, if the value is changing, the changing value here, it will get affected here also. So you don't go and disturb this thing, right? So Thevenin network you have to find. So first one is marking the networks. So this entire thing will be my network. So it is network, and I'll just put my reference node as well. All right. Second step is to find VOC, which is the open circuit voltage. In this case, it is nothing but Vx. All right, and that will be going to be a Thevenin voltage. Now this Vx will be traveling here because there is no drop here. So this voltage will be same as the voltage here. So it is Vx here. Now let us go around and find the value of Vx. So I can use a node analysis here. So Vx minus 4 divided by 2. All right. Now I always put 2 because this was in milliamperes. But now this is not in milliamperes. They have not specified it as milliampere. That means it might be a ampere value. Therefore, I have to put the total value. I have to convert it into proper SI system. All right. So don't make this mistake. In case they give in milliamperes, you can do it directly. Otherwise, you will get a wrong result. So put it 2000. So minus Vx by 4000. All right. And this current will be 0 to 3K. So this is equal to 0. All right. So what I will be getting? I will be getting the Vx to be equal to 12 divided by 5 volt. And this is nothing but the open circuit voltage, and this is nothing but the Thevenin voltage 12 by 5. The next procedure, next step is finding RTH. So you have to find the value of RTH as seen from this direction. Now you can actually go around and you can kill this independent voltage source. But this independent current source you cannot kill. You cannot. The only sources that you can kill are independent sources. You cannot go and kill this dependent source. So now you are in a fix, right? How you will find? Because earlier you directly found out that 2 plus 3 was equal to 5. Now what you will do? So here is that definition which we learned will come into handy. So here I am going to put this voltage which was equal to 4 volt. Let it be there like that. All right. Now we have already learned RTH is equal to the Thevenin voltage by the short circuit current, or this is the Norton current. All right, same, both are same, equal to Norton current. Now Thevenin voltage already you have found to be 12 by 5. Now how to find the short circuit current? Remember the steps. All right, let us remember the steps. What you do is that you, all right, Vx is there, don't forget the Vx is always there. You replace this point here by a short circuit, and this will be the short circuit current, and this terminal voltage was Vx. All right. Now to find ISC, I will have to use a nodal analysis, right? I have to use a nodal analysis. So I'll just replace this by V, because this voltage is not going to be same, because now you have made a short circuit there. This current will be flowing. So let this be voltage be called V. So I will use a KCL here. So V minus 4 divided by 2000, all right, minus Vx divided by 4000, all right, okay, and this plus ISC equal to 0. Now we are in a very terrible fix. You are having, you don't know V, you don't know Vx, and you don't know ISC. You are having so many unknowns. But look at the circuit carefully. What is the value of Vx? Vx is this particular voltage, right? It is this particular voltage across this wire. Now across a wire there is no resistance, so across the wire the voltage drop will be equal to 0. Therefore in this particular case, when you short this thing, Vx is going to be equal to 0, and that will affect this dependent source here. So Vx is going to be equal to 0 from the circuit. Alright, in any circuit you will get clues like this. So if I substitute that here, so V minus 4 by 2000, this will go, Vx is going to go away, plus what is the ISC value? It is V divided by 3000, that will be equal to 0. Okay, that means in this case the value of V will be equal to now this is the problem in which I am interested in, because this has a dependent source. All right, and this particular this thing is Vx here. Now you have to find the Thevenin equivalent of this particular circuit. This is an interesting question. All right, this is going to little bit challenges. So let us see what we have to do. So as the procedure tells us, first you have to identify the networks. So this entire thing is going to be our network, right? So this entire thing is our network. And next one is finding the open circuit voltage, which is equal to the Thevenin voltage. So here already the circuit is open circuited, and you already defined a voltage there, which is Vx, and therefore the open circuit voltage will be equal to Vx, right? So next is what we have to find, what is the value of Vx. So I will use my node analysis technique because I like node analysis. Now clearly, because there is no current which is flowing through this resistor, because this is an open circuit here, the voltage across this terminal and this terminal will be entirely exactly the same. So this also will be equal to Vx. In case you have doubt, you can just put some voltage here plus V, and you can see minus V plus Vx will be equal to 0, and therefore Vx equal to that small v here. Now let us apply KCL. So Vx minus 4 divided by, now I always put 2 here usually in these problems. That is because this particular current used to be in milliamperes, but in this case they have not given it to be in milliamperes. All right, they have not given to be in milliamperes, they have given it to be in amperes, or you have to think that they have to give it in amperes, right? Because if it's in milliampere they would have told it specifically, but they've just directly given it like this. So you have to follow SI units. So I have to put here 2000, 2k is 2000 ohms. So and minus Vx by 4000. All right, and here there is going to be no current, so plus 0 equal to 0. Therefore in this case, when I solve this particular circuit, if I make a quick solution, what will I get? I will get here 2Vx minus 8 minus Vx, right? So the Vx will be equal to plus 8 volts, and that will be equal to my open circuit voltage, and that will be my Thevenin voltage. Third thing is to find the RTH. All right, so where do you have to find the value of RTH? RTH, you have to find it across this area, and this is Vx already given. Now I can go around and kill this circuit. So by killing I mean that I am shorting the voltage source, but I cannot short this dependent current source. You can only short, or you can only kill independent sources. Dependent sources you cannot kill because they are always dependent on other parameters. Therefore now in this case I cannot solve it using a direct resistance technique. These are not in series, not in parallel. I am confused now. I don't know what to do. All right. So what we have learned in the previous session is that The RTH value is nothing but the Thevenin voltage or the open circuit voltage divided by the Norton current or the short circuit current. Alright. Okay. So this information we are having. So let us see if we can find using this particular information. So let me redraw this voltage source. So this was 4 volts, right? Now VTH already you have found it is 8 volts. Now the next thing which you have to find is the ISC. What was the procedure to find ISC? The procedure to find ISC was you take the terminal A, it is this open circuit terminal, and you short it, alright, and this particular current, I'll just make it with a different color, yeah, and this particular current ISC is the short circuit current, right? Now let us write the node equation again. Let us try to find the value of Ix. Now, this voltage will be V. This is not same as Vx because now you are having a resistance and a current will be flowing here. So there will be a drop. Okay. Now let us apply and let us see what we get. So I get, applying KCL, I get V minus 4 divided by 2000, alright, minus Vx divided by 4000, alright, and this particular current is nothing but V divided by 3000. I can put ISC itself, but ultimately I am going to anyway put V by 3, so I am directly writing it, alright. So equal to 0. Now we are having one equation and two unknowns. What is Vx now? Does the circuit give us any clue about Vx? Now let us look at closely here. Vx is nothing but the voltage across this particular short, right? This wire. The wire does not have any resistance, therefore it will not have any drop. Therefore this Vx should be equal to 0 volt in this case. That means in this case Vx will be equal to 0 volt. So V minus 4, so Vx, this term will go 0 plus V by 3000, alright, equal to 0. That means in this case if I solve this, I will be getting V to be equal to plus 12 divided by 5 volts. Alright. Now that you have got the value of V, let us go and find the value of the RTH value. Alright. Now now that you have found out the value of V, I can find the value of ISC, which is equal to V divided by 3K. Alright, now notice that I have put 3K here. So it is equal to 12 divided by 5 divided by 3. So this will be giving me 4 divided by 5. This will be in milliamperes. Be very careful with the current values, because in competitive exams like GATE, you will be getting the options as milliamperes and they will expect that you have put it in amperes and they will put it in that way also. So you have to be very careful while writing all these units here. Alright. Now once you have found out the value of ISC, RTH is very easy. RTH will be equal to VTH divided by ISC, and VTH I have already found out to be 8 volts here. So it is 8 divided by 4 divided by 5. Now that will be giving me 10. What is 10? Now this is milliamperes, right? And this was volts. That will be 10 kilo ohms. Alright. Now that I have found out the value of VTH and RTH, the only step that is remaining is to put the Thevenin equivalent circuit, which is the series voltage source and the series resistance of RTH. Alright, so this is the equivalent. So I've replaced this entire circuit which was given to me like this into a simple circuit, and the Thevenin voltage is 8 volts and the Thevenin resistance was found to be 10 kilo ohms. I hope you have understood this lecture of how you can use dependent sources. I hope you have understood this lecture of how to approach the problem, how to find the Thevenin equivalent, Thevenin resistance when the dependent sources are involved. Alright. So I hope you enjoyed this lecture, and please keep watching the videos to improve your knowledge on engineering circuit analysis, and I will see you in the next lecture. Thank you.